Greetings. We will continue our discussion on the atomic photoionization process, and in particular we will develop the expression for the photoionization cross section, and it is very complicated to get the exact expression, but we will develop the expression in some approximate limit which is known as the Born approximation. So we got the expression for the differential cross section in our previous class, which I refer to over here, and remember that this transition rate W has got a Dirac delta function over here. So you must remember that the Dirac delta is a quantity which has got its own dimensions, and you must plug in the dimensions of the Dirac delta correctly so that you will get the correct dimensions for the differential cross section. I have been referring to this sometimes, and it is important that you get the correct dimensions. So here we have inserted the expression for this transition rate in this expression for the differential cross section, and notice that there is the square of the amplitude of the intensity, square of the amplitude of the wave electromagnetic radiation, and you have it in both the numerator as well as the denominator. So these two terms will cancel each other, and the rest of the expression is what we have written over here. So the A0 square is gone, and by a slight rearrangement of these terms, by taking these term omega square and twice pi c to the numerator, you rewrite it in a somewhat convenient form and extract the fine structure constant E square over h cross c. Q is the charge, so Q square is the same as E square. So extract the fine structure constant from this h cross c, and then you still have an h cross square over here. So this is why an h cross square over h cross was written over here. You have only one power of h cross in the first expression, but this allows us to extract the fine structure constant, which is the common form in which you will find it in literature, that the differential cross section per unit solid angle for a given incident direction which is polarized along the unit vector epsilon for photoelectron ejection in a unique exit channel which is along the wave vector kf is given by this expression, right. So that is what we get for the differential cross section. Now here this omega tilde is the difference between these two frequencies, okay. Now you can write this Dirac delta as in terms of the energy difference as well, because this frequency being equal to the resonant frequency, this condition is precisely the same as the energy of the electromagnetic radiation being equal to the energy difference between the initial state and the final state. But the dimension of the Dirac delta for delta omega and delta E are obviously different, right, which is why you have an h cross cube over here as opposed to an h cross square in the previous step, okay. And this is really important because in different books, whether you look at Sakurai's book or Schiff's book or Landau Lifshitz and so on, sometimes you find the differential cross section to be written and you find a term in h cross square, and sometimes you find a term in h cross cube, and obviously you have to keep track of the exact power. And in some literature the Dirac delta is not explicitly even written, because it is understood that the transition will take place at a precise resonant energy corresponding to the energy difference. So you have to see what the author has in mind and then make sure that you get the correct expression for the dimensions. This dimension, when you take all the dimensions correctly, it will affect not only the dimensions but of course the numbers, because you have got an extra h cross over here. So your answer will neither be correct numerically, nor will you have the correct dimensions for the physical quantity that you are evaluating, and it would be absurd. So make sure that you always keep track of the dimensions, and here you will have the dimensions of L square. So, it is a cross section, it has got dimensions of area, and it is usually reported in units of 10 to the minus 18 centimeters square, which is called as a megabarn. So, that is the unit in which the cross section is usually reported, and 1 megabarn is 10 to the minus 18 centimeters square. So, now this is the process that we have considered. We have got the photoelectron which is ejected along this wave vector kf, but then remember that in this direction there may be other states, other energy states which are degenerate with the energy at which the transition is taking place, and therefore, this is not a unique transition. There will be scaling, because there will be, if there are additional states which are at the same energy where photo ejection in the same direction can take place, then you will have to augment the expression for the differential cross section by the number of states which are available. So, we have to figure out a mechanism to estimate this number of additional states, so that we get the correct scaling factor. Okay. So, all states which contribute to photoionization, they will all contribute to this matrix element if they are at an energy which is degenerate with this at this particular angle of ejection. Then what we have to do is to find out this number. So, how do we find out this number? So, what we do is we have to construct a grid of points, okay, so that each of these axes, like x axis, y axis and z axis, instead of looking at them as length axis, we consider them to be 3 orthogonal axis in the number space. So, you have got nx along one axis, ny along the orthogonal axis, and nz along the third axis, and then you construct a grid of points. So, you have got the origin at 0, and then you construct a number of points. So, you have got 3 orthogonal number axes, and then you can go ahead and put additional points at not just 0, 1, 2, 3 on the nx axis, but then when nx is equal to 1, ny is equal to 1, and z is equal to 1, and so on. So, you get an additional number of points in all coming from all the 3 axes, right. And then all of these points which belong to that unit volume which I showed in the previous figure, okay, all of these points which correspond to that unit volume in the previous figure. So, those are the number of points which will contribute to the photoionization process, and the differential cross section will have to be augmented or scaled by this factor. So, how do you calculate that? So, you know that the volume element along this axis is given by this r square dr solid angle sin theta d theta d phi in the spherical polar coordinate system, right. And here instead of r you have n, okay. So, where n, it is a discrete number, it is not a continuous variable like distance, but for all practical purposes, because all of these points are very densely packed, okay, you can treat it as a semi or a quasi discrete, you know, kind of parameter. So, the number of points that you are really talking about, the number of states which belong to this volume element, will be not r square dr d omega, but n square dn d omega, okay. So, that is the number of states which are available for this transition, and each of these will contribute to photoionization corresponding to the same matrix element, because they are all having the same physical energy. So, they are all degenerate processes, and they will actually augment the differential cross section. So, to get this number n square d n d omega, we make use of box normalization, and this is tentative. One can use other ways, one can do other normalization. We have used Dirac delta normalization, but you can also do box normalization. Our end results will be independent of the normalization. So, you will find that the normalization really goes off in the final analysis, but so this is just a tentative steps, and we just use the usual Born von Karman boundary conditions and ask how many wavelengths fit into the box, because you have these continuum states, okay, which are not square integrable. So, we will do a box normalization for these states, and because of this boundary condition you have the wave number k, which goes as 2 pi n over L for each dimension x, y and z. So, your energy at which this physical process is taking place, which goes as h cross square over 2 m, and k square is kx square plus ky square plus kz square, but kx, ky and kz are now given in terms of nx, ny and nz and the size of the box. Okay. So, this is what allows you to write the energy as n square times the rest of the constant factor. Okay. L is the length of the box, but it will disappear from our final result. So, this is the number of states in this volume element that we must use. Now, we need to find what is dN by dE. Now, dN, as I mentioned, this is being treated as a quasi discrete parameter. So, to get dN by dE, you recognize that E goes as n square. So, that lets you determine dE in terms of this is the differential in energy. So, this will be twice n dN coming from this n square, and now you have dN by dE, which you get from this expression by turning this around, and dN by dE goes as various constants, and then I have extracted the 1 over n. I have written in terms of k over n, but then k is cancelled by this 1 over k over here, because this factor m over h cross k is given by dk over dE, because for a free electron this is the relation between k and energy. So, dk over dE for a free electron turns out to be m over h cross k. So, you can write this not just as dN over dE, but you get dN over dE in terms of dk over dE, and you will see that this gives us a certain convenience. So, dN over dE is what you get from here. So, dN over dE comes out in terms of dk over dE times the other parameters, but there is this k over n that sticks out, and you need this k over n, and you get the k over n already because you have this expression between n square and k square. So, k over n is nothing but twice pi over L. So, you use this expression for k over n, and this is twice pi over L, and now you have got an L square over 4 pi square and a 2 pi over L. So, that gives you L over 2 pi. So, this is the expression for dN over dE that should go over here. Okay. So, we have put that in over here, and given the fact that n square goes as k square, this n square is now written as L square k square over 2 pi. So, that is the only substitution over here. It is a very straightforward substitution, and now you can combine this L over 2 pi over here with the square of L over 2 pi. So, that gives you a cube of L over 2 pi, and then you have k square dk over dE du omega, and given again the fact that dk over dE, as I showed in the previous slide, is nothing but m over h cross k. So, you can write this over here, and then you can always simplify this so that you have the cube of L over 2 pi, and then you have one of the powers of k cancels this in the denominator. So, you have got 1 power of k in the numerator. So, you get m k over h cross square dE over d omega. So, this is a matter of some detail, but it is important to do it right. So, once you put in this n square dA and d omega which we have found, we need to add up the contribution due to all of these states which are degenerate with respect to the physical process that we have in mind, right. So, you have to add up, and addition is integration. So, that is what we have done over here. You have got this Dirac delta, okay. This integration is over the energy, and you can carry out this Dirac delta after scaling it by this additional factor, okay. And now you do a Dirac delta integration over this. So, you will get, how Dirac delta function is done. So, you will get the integrand only for the particular value of E corresponding to EFI, right. So, that is the only term which will contribute, and that is what you get over here. So, E equal to E Fi will correspond to omega equal to omega Fi. So, I am now putting a subscript on this omega, which is coming from E equal to E Fi, and then you have some of these additional terms. So, this is the expression for the differential cross section per unit solid angle, and it already takes into account the augmentation due to the additional number of states which are degenerate with respect to energy at which photoionization is under consideration. So, now we are going to have to take some specific interest in this matrix element. This is the matrix element of this operator between the states I and F, which I have written as M. You have the square of the modulus of M, which I have written here, okay. And we will discuss the implications of this matrix element, which is the transition matrix element for the transition for the initial state to the final state. Now, notice that this matrix element is essentially a space integral, right. This is the Dirac notation. It is essentially an integration over space. So, let us write this explicitly as a space integral, and now you have the continuum state, which is again box normalized. So, you have got the 1 over root L cube coming for this, okay. So, you have got the continuum state F as e to the minus I k f dot r, and then you have got e to the I k dot r, which is over here. You have epsilon dot del, and then you have the initial state wave function. Now, I do not know if some of you are beginning to recognize the form of this function, because it is developing into an integral which is a very famous expression in mathematical physics. So, this is the matrix element, and you now extract this 1 over root L cube outside. You have got the rest of the integrand, okay, and in this integrand you have got the momentum operator gradient. So, to write this del operator as a gradient operator, I multiply it by minus I h cross, and I also divide it by minus I h cross, okay. So, that in the matrix element you recognize that you really have to get the matrix element of the momentum operator, okay. And now that you have got this gradient operator in the integrand, this is the momentum operator, which is a Hermitian operator. So, you can have it operate on the right or also on the left effectively, right, and it is a lot easier to operate on the left, because we know what is the gradient of this k minus k f dot r, okay. That is a very simple derivative of an exponential function. So, you have it operate on the left rather than on the right, and then when you do that, when you operate it on the left, you get epsilon dot I k minus k f, okay. This is the k minus k f. So, this is the term which is coming in when you operate it on the left, and you have them to multiply by this psi I, which is written over here. So, this is the matrix element, and now epsilon dot k minus epsilon dot k f is what you need, out of which epsilon dot k is 0. K is the direction of propagation of the incident electromagnetic radiation, right. Epsilon is the polarization, which is orthogonal to that. So, epsilon dot k is 0, and now instead of this k minus k f, you only have epsilon dot k f. There is a minus sign which I have written over here, okay. So, this is your expression for the matrix element. Now, this is epsilon dot k f. Now, photoionization takes place in a unique direction, okay. So, epsilon dot k f with reference to this particular unique exit channel is a certain constant cosine term which you can pull out of the integration sign, and the rest of the integral you will see that you need the cosine of this angle other than the magnitude of k f, of course, but then you will need the cosine of this angle, and then you will have to evaluate this integral, okay. So, what is the cosine of this angle? This is the angle between the polarization vector which is along the x axis, and k f is the direction of ejection. So, you can get it easily by taking this unit vector is along E x, this is along the spherical polar unit vector E r, right. So, you can write ER in terms of Ex, Ey, Ez and then take the scalar product of ER with Ex. So, you see that this cosine term is nothing but sin theta or cosine phi. Okay. So, that is what you get for the cosine term, and now you can use this cosine term in the expression for the matrix element. This is what we have determined, this cosine term. This is sin theta cosine phi, and this is cos square omega when you take the modulus square, right, and then you will have to take the square of this integral as well. So, this is I put the whole integral in this rectangular square bracket, and then I take the square of it when I take the modulus square. So, you get an L cube over here, and you can see how the box normalization L cube will cancel what we had originally started out with. So, the integral that you are looking at, this is essentially the Fourier transform of the initial state. Okay, this is what I had hinted, that it is developing into an integral which is very commonly used in mathematical physics. This is nothing but the Fourier transform of the initial state, and for any initial state all the hydrogen atom 1s, 2s and so on, all these functions are well known. You can get their Fourier transforms very readily. So, that is a result that you can plug in straight away. So, what you can do is, just for the sake of our consideration, the initial state could be any initial state with quantum numbers n, l and m. Just to illustrate this the physics which is contained in this expression, I will use photoionization of the hydrogen atom in the 1s state. So, this psi n l m is nothing but the 1s state of the hydrogen atom, and what you need is the Fourier transform of the hydrogen atom 1s state. So, this integral, which is the Fourier transform of the 1s state of the hydrogen atom, this turns out to be this, which is a matter of mathematical detail. It is just a matter of getting the Fourier transform of the 1s wave function. So, this is what the Fourier transformation gives you, and we will use this result in getting an expression for the matrix element. Okay. So, the matrix element square is what you need. You have this integral which needs to be determined. Okay, this is the Fourier transform, and this integral, which is the Fourier transform, is having this form. So, you will plug in this integral in the expression for the square of the modulus square. This will go over here, which will go into the expression for the differential cross section. So, it is just a matter of substituting the corresponding terms. So, that is what we are doing. Okay, so, let us do that. Once you put in the Fourier transform, okay, the differential cross section, and I am carrying this information about the direction of polarization and the direction of photo ejection by writing this superscript and subscript over here. Okay. So, this is a complete expression that you get. Notice that this L cube will cancel L cube. So, the size of the box really does not matter, and the box normalization that we had done, there is nothing arbitrary about it, because it really does not matter. So, now you can cancel all the terms, and then you have various terms that you can combine. So, L cube cancels L cube, and you had a 64 over here, but there is a 1 over 2 to the power 3. So, there is a 1 over 8 here. So, this 64 by 8 into 4 is what gives you this 32. Okay. So, you get this 32 alpha h cross, then there is a kf cube coming in. Okay. There is a k over here, this is taking place at the resonant frequency, right. So, you have got a kf cube over here, and you have got the cos square distribution as we have noted already. Okay. So, you have the fourth power of this term in the denominator, and then we can develop an approximation which is known as the Born approximation, and in the Born approximation this expression gets a very simple form. Now, what is a Born approximation? Typically, the Born approximation is employed when you are dealing with high energy processes. Okay, when you have a fairly large energy which is absorbed by the atom and the electron is knocked out. So, when it comes out, it has so much of excess energy that it goes out very fast. and this is a nice case to consider, because if it is coming out very fast, then it is not going to have enough time to have correlations with other electrons to be expressed in the dynamical process. So, the independent particle approximation is also a good approximation. Usually, by and large, this is something which has to be qualified later, but by and large the Born approximation is a good approximation. It justifies the independent particle approximation. You expect it to work at high energies, okay, because that is when the kinetic energy of this photoelectron is much larger than the ionization potential. Okay. So, if the physical process is taking place, for example, like 1000 eV, okay, and the binding energy is like, it is of the order of 10 eV, like 13.6 eV for the hydrogen atom, right. Then the kinetic energy with which the electron comes out is much larger than the ionization potential, and this energy of the electromagnetic radiation is almost equal to the kinetic energy, more or less, given the fact that you are ignoring the small difference. Okay. So, h cross omega in the Born approximation is nearly equal to h cross square kf square by 2m, which tells you, if you cancel one power of h cross from both sides, you have omega equal to h cross k square by 2m. So, this is the Born approximation. Omega, of course, is k times c. Therefore, you have k times c, which is nearly equal to h cross k square by 2m, and this tells you that k over kf will be equal to Vf over twice c, c being the speed of light, which you know is huge. Okay. And in the Born approximation, k over kf then becomes a small quantity, which in some approximate expansion scheme you will be able to ignore. Okay. So, this is the advantage of the Born approximation that we will exploit. So, k over kf is much smaller than 1. This is when the Born approximation holds for high energy processes, and the other quantity that we need is the square of the modulus of k minus kf. So, that we will get by taking the scalar product of these quantities, and you need again the cosine of the angle theta. Theta is the angle between k and kf, which is a polar angle in our spherical polar coordinate system, right. Kf is this k, our choice of z axis is along the incident direction of electromagnetic radiation. So, this is cosine theta, this is the polar angle theta, and you can now get kf square, factor it out, because you have an approximation for k over kf. So, it is good to factor out kf square, and where you have k over kf square, you can make an approximation which being Vf over 2c, which is a small quantity. Okay. So, you can ignore this term and you have the rest of it, which is kf square times, this becomes ignorable compared to 1, okay, and then the rest of it is 1 minus Vf over c times cosine theta. So, these are some of the details of the Born approximation, and we can use this expression over here, where you need the modulus square of k minus kf, which we have shown to be nearly equal to kf squared. That is nearly equal to is within the premise of the Born approximation, and you have in the denominator z square plus a0 square times the square of this modulus. The square of this modulus is now written in terms of this kf square times this, right. So, you have got 1, 2 and 3 terms on the right side. So, those are the 3 terms on the right side, but then this kf, which is proportional to the momentum of the ejected electron, and this momentum is very high, okay, because we are working within the premise of the Born approximation. So, because this momentum is very high, this term is much larger than z square. So, you can ignore this z square compared to this. This is the high energy approximation that we are working with, this is the Born approximation, and within this approximation this left hand side is nearly equal to this right hand side, but this right hand side out of the 3 terms, the first one drops out and you have the remaining 2 terms which you can use in your expression for the differential cross section. So, using that you have this A0 square kf square, these are the remaining 2 terms which will go over here. You had the 32 alpha h cross k cube by m omega coming from the previous expression for the differential cross section, and now you have this 1 minus v over c cosine theta to the power 4. Okay. Now, this again you can expand and develop an approximation because v over c is small, right. So, let us do that. So, you have got 1 minus v over c cosine theta to the power 4, you need the 4th power, you have got the cos square of gamma distribution, and this we have already seen to be equal to sine theta cosine phi, you have got the square of this. So, the differential cross section per unit solid angle in a given direction for photo ejection has got this cos square phi distribution, it goes as the square of the cosine of the azimuthal angle with respect to the zx plane. So, this is an extremely important result in photoionization physics. Now, if you had unpolarized light, so instead of this epsilon you need to develop an expression for the unpolarized light. So, all you have to do is to use the average value of cos square phi, okay, because that azimuthal angle will lose its significance. So, you need to use the average value of this cos square phi, which is 1/2, right. So, for unpolarized light this expression for the differential cross section is half of this. So, instead of 32 alpha h cross you get 16 alpha h cross, rest of the expression is essentially the same. This is the expression for the unpolarized light, and notice that you have got 1 minus v over c cos theta to the power 4 in the denominator. So, in the numerator it will come as 1 minus v over c cos theta to the power minus 4, and if you expand it and take the leading term you get 1 plus 4 times v over c cos theta, okay, that is the leading term of that expansion. Alright, so now we almost have the final result that the differential cross section is given by this 1 plus 4 v over c cos theta, and now you can do an integration over angle because this is the differential cross section at a given polar angle theta. What if you get the total cross section, that is to allow for photo ejection in all directions, and that will require you to integrate over theta going from 0 to pi and the entire solid angle. So, when you carry out this integration there are 2 functions of theta over here, sine square theta, and there is a cos theta over here. So, when you do this theta integration this is the result that you get, it goes as z to the power 5 and a0 to the power 5, you get 1 over k to the power 5, and what is k to the power 5? K to the power 5 you get in terms of energy because energy is nearly equal to k square, right. So, the 5th power of k will go as the 5/2 power of frequency, right, because the 2nd power of k goes as energy. So, the 5th power of k goes as 5/2 power of frequency or energy, and 1 over kf cube goes as the denominator of this term on the right, and you get the expression for the total cross section for unpolarized light, which goes as omega is here, there is omega to the power 5/2 coming from this kf to the power 5. So, omega to the power 5/2 plus 1 power of omega will give you a power of 7/2 in the denominator, right. What it tells you is that the total cross section is inversely proportional to the 7/2 power of the energy in the Born approximation. Okay. So, this is an extremely important result. It goes as e to the power minus 7 by 2. This is an extremely important result in photoionization physics, that if you want to have a first estimate of how will the photoionization change with energy, you know that it is going to decrease with energy, but at what rate does it decrease with energy? So, it decreases at the rate of e to the power minus 7 by 2. It also goes as z to the power 5. So, when you are doing hydrogenic atoms with large number of protons in the nucleus, right, it will go as z to the power 5. We have done this calculation just to illustrate for the hydrogen 1s state, but you can do this for any other state of the hydrogen atom. You can do the NLM and you will require the corresponding Fourier transforms. When you do it for an arbitrary quantum number, it will turn out, and that is something which I am not going to illustrate over here, but I will use the result that when you do it for arbitrary n, it goes as n to the power minus 3. Okay, that does not come explicitly for the hydrogen 1s, because n is equal to 1 in this case. So, this is a very important result, that the total photoionization cross section for unpolarized light goes as e to the power minus 7 by 2, it goes as z to the power 5 and n to the power minus 3. There is nevertheless a breakdown of Born approximation. This is a matter of detail. One believes or one hopes that okay, this will always work at high energy, but then it turns out that there are certain detailed correlations which really cannot be ignored even in the Born approximation. So, Born approximation that you expect to hold very well in the at high energy, and you hope to use it in the independent particle approximation, which you hope will work in the Born approximation. It really does not happen, because there are certain correlations which survive even at high energy. So, this is a matter of detail, but by and large it is an excellent approximation, and you can look up some of these details in literature. So, this is where I will conclude today's discussion, that you have the expression for the differential cross section, and we will then have to discuss some specific aspects of this matrix element. And notice that this matrix element has got the gradient operator, it is the momentum operator, and then this form of the matrix element is sometimes called as the momentum form of the matrix element, but then you can also get what is called as the length form of the matrix element. So, some of these details I will discuss in the next class. So, I will conclude today's discussion over here, and we will discuss the length form and the momentum form of the matrix elements and the oscillator strength sum rules and so on. So, that will be the topic of discussion for the next class, but the important thing over here is that the total cross section goes as energy to the minus 7 by 2, z to the 5 and n to the minus 3. So, these are very important results in photoionization physics. If there is any question, I will be happy to take. Very well, thank you.